Hello friends, welcome to our channel Physics for You, and today in this video we are going to learn about one of the practical, that is torsional pendulum. Okay, as you can see on the graph, as you can see on this practical journal, the torsional pendulum actually it is one of the pendulum used to find the modulus of rigidity of a given wire. That means if you have a wire, metal wire, thin wire, and of which we want to find the modulus of rigidity. So we know modulus of rigidity and Young's modulus and bulk modulus, all are these are the force constants, and in one of the previous video we have seen about the Young's modulus using cantilever. So here similarly we have to find the torsional pendulum, means using torsional pendulum we have to find the modulus of rigidity. It is denoted by eta, right? That is what our target. Now as you can see on the journal, the aim is what? To find the modulus of rigidity of experimental wire, whatever may be the wire given to you. And yes, we required this apparatus, experimental wire, circular disc, screw gauge, lamp and scale arrangement to measure the oscillations, right? Now this is what actually the formula using which we have to find the value of eta. So this eta stands for modulus of rigidity. It is equal to 4 pi L r square m divided by t square and small r power 4. So actually L is what here? The length of the experimental wire. R is what? Radius. Okay, let me show you the diagram how the torsional pendulum looks like. So this is what? The fixed end actually. Here we have a fixed end, and this is the disc, and this is actually the experimental wire whose length is L. Let us consider. So L is the length of this experimental wire. Capital R is the radius of this disc. Time is what? Time required for one oscillation, or we can say the time period of oscillation. Then mass, capital M in the formula, it is actually the mass of this disc. So here we are going to use the disc of mass 1150 gram. 1150 gram. And small r, lastly, it is the radius of this wire, whatever may be the radius of this experimental wire, that is denoted by small r. Okay, so this is what actually a simple experiment using we can find the modulus of rigidity of the given experimental wire. So as you can see in the diagram only, you might got the idea. We have to fix the experimental wire, one end of the experimental wire we have to fix at some point, and to the other end we have to attach the solid disc. And here I told you the disc we are taken here is of 1150 gram, that means it is more than 1 kilogram, right? So we have to attach the disc to the other end, and so that we have to check at the same time that disc can rotate, that disc can take oscillation in horizontal plane. Now see here how will be the arrangement actually. So if this is the wire, actually this is the wire. Now I can say this is the wire, one end is the fixed and other end is fixed to the disc. Now let us consider this is the disc. So we have to keep in mind that this end should be fixed, but the disc in other end, which is fixed to the other end of the wire, should oscillate in this horizontal plane, right? Because we have to check the oscillations and it's a time period, so therefore disc should oscillate. So one of the end of the wire will be fixed and other end is fixed to the disc, which can have some oscillations in horizontal plane. Okay, and we know that due to that what happens, a twisting will happen in the wire. Now let us consider, I am talking about this. This is the wire. Now I will show in this horizontal manner. So this is the fixed end, and now here is the disc is attached and disc is rotating in this way. So the wire will have some twisting, wire will get twist because one end is fixed and other end we are applying a twisting couple force, we can say. So whenever there is a twisting, then we can have the modulus of rigidity, or moreover it is also known as shearing, right? So that is what actually the definition of our modulus of rigidity. Eta is equal to shearing stress upon shearing strain. Yes or no? Shearing stress upon shearing strain. Shearing strain. What is this shearing actually? Shearing means, yes, since this is the fixed end and due to the rotation what happens, the other end will have some twisting. Now I will draw the twisting likewise. So this is what the angle theta, right, that is also called as twisted angle or twisting couple also. So that's what happen, and there we can find the modulus of rigidity of that particular wire. So how many observations are we required here? Yes, first of all we have to check the length of wire, then radius of the oscillating disc, then time period, then mass which is already given, and we have to measure the radius of the experimental wire. So theoretical part, here we are just talking about the strain, stress and all these things, okay, that we can see in later also. Now the procedure, in procedure same whatever I told you, that is only the procedure. One end we have to fix to the or a wire we have to fix at some point, and to the other end we have to attach the disc, and so that that disc can oscillate in a horizontal plane. So how to do the observations and how to find the time period? So here simply after attaching the disc, because now the mass is also fixed, so we have to take the 20 oscillations, and whatever may be the time required for 20 oscillation we have to note down in 3 different cases, right, or we can say 3 different trials we have to take. And yes, we can write here it as T1, this is the second trial T2, and this is the third trial T3. Don't see these readings, these are what the for just practice purpose. So T1, T2, T3, these are the 3 trials we have to take. As we know, for the accuracy we will take generally 3 trials, and then mean of these 3 will be the mean time, which is yes again in seconds, all these times are in second. And after dividing, because what this mean time is what time required for the 20 oscillation, right. Again we know oscillation how to measure while doing the experiment only. I will tell you how to measure the oscillation. So likewise we have to measure the 20 oscillations, and this mean t is what the time required for 20 oscillation, but we want in formula time period, that is capital T. So obviously it is the time required for one oscillation, that's why we should divide this mean t by 20, and yes, this will be the time period in second, and that is what actually the time required for one oscillation of that disc. Once you get this capital T, yes, nothing else, next capital T is we have to substitute in this formula, and yes, other calculations we can, or other observations we can do. We can measure the length of wire by the scale, meter scale, radius of oscillating disc, that is again one of the thing we should talk about. So radius of oscillating disc, how we have to measure? If this is the disc, we have to take on thread, a wire or a thread, and yes, to the oscillating disc we have to just first of all measure its circumference by using a thread. So take a thread and make it completely round to the disc, and then make it straight. After making straight, just measure this. This will be what? 2 pi r. Yes or no? This is what? 2 pi r. If r is the radius, then this is what? 2 pi r. And if 2 pi r is equal to something centimeter, then by using we can find the r. So that will be the radius of the disc, and mass is given, and radius of the wire. So for this wire we have to find the radius by using screw gauge, because the wire is very thin, and for such a thin bodies we can find its radius by using the smaller measurement apparatus, and that is what? Screw gauge. Okay, so after substituting all these values in this formula, we can find the modulus of rigidity of given wire. So friends, let us go to the experimental part, and then we will see the calculation part, right? Okay, now come to the experimental part of this torsional pendulum. As I told you in the chart discussion, torsional pendulum is actually a disc, a solid disc which is fixed one of the end to the wire, and other end of the wire is fixed. So such an apparatus or such a pendulum, and which can free to oscillate in horizontal plane. If you remember, we have talked about the horizontal plane, and as we have seen in the previous experiment in cantilever, but the cantilever is taking oscillation in this vertical plane. But what we require now, yes, it should take the oscillation, disc should oscillate in horizontal plane, and that structure, that particular apparatus, we called it as the torsional pendulum. Now see here, the wire is fixed, and now the disc can oscillate in horizontal plane. I hope you can see the disc is oscillating in horizontal plane. It should not have some deflections in the vertical plane. So this is a metallic wire, and now what is the target in this particular experiment or in this practical? We have to find the modulus of rigidity of this material of experimental wire. So we have taken here a metallic wire, and let us consider we don't know of which metal it has made up, but once you know its modulus of rigidity, then you can directly compare yes, of which material it should be made up of, right? So for that purpose, or different engineering and industrial purpose, we require the modulus of rigidity, Young's modulus of that particular metal or material. So this is what the simplest method to find the modulus of rigidity. Now this Ketter's pendulum, sorry, the torsional pendulum, we have to measure the oscillations again. If you remember, we have to start the stopwatch, right? And similarly, while taking 20 oscillations, how much time is required, that is what we have to do here also. That means ultimately we have to find the time period for the formula. Moreover, we require the length of wire also. So by using this thread, I can exactly measure the length of the wire. So this also we require small l, right? So this is what the length of the wire, whatever may be the part of wire you can see, that is exactly you have to measure. So just keep this length on your meter scale and measure, that will be the small l length of the wire. Similarly, we want to find the radius of this disc, radius of this disc. So if you remember, I told you again, by using this thread, first of all get the circumference, right? So this is what I am just what we can say, attaching this string around this particular disc, and yes, I got this much is the circumference. Now just keep this thread on your meter scale and again measure it, how much is with the centimeter, that is equal to 2 pi r. We know circumference is 2 pi r, and from that you can get easily capital R, that is radius of the disc. But one more thing we require, and that is what, radius of this wire. Now see, already this wire is very thin and we have to find its radius. So by using some our what we can say normal tool, it is not possible. So again we can take the help of our screw gauge. So this is what made for such purposes only. We know its least count is 0.001 centimeter, that means such a small value we can measure. So again, to measure the radius of this wire, first of all we should find the diameter. Now because I am attaching to this wire from outer side, that means I am finding first of all the diameter, right? Firstly we will find diameter. So this is what the smallest diameter, so on which this we have one main scale and circular scale. So take the reading, and moreover for the accuracy we will find diameter at 3 different places. I will find first of all here, then here, and then here. So as we got 3 different readings, first then find the mean of that 3 diameters, that will be the total diameter on mean diameter, and yes, divide it by 2. So what we will get, the radius of this particular wire. Okay, right. Now these are what the observations. Now let us talk about the reading, or how to take the reading to find the time period. Yes, what is the next tool, or what is next thing we require? The capital R is over, small l is over, small r is over, 4 pi is a constant. Now next is what, only the time period, and one more is there, mass of the disc, but already we know the mass of this disc is 1150 gram. Okay, so to find the time period we have done this arrangement. That particular arrangement is called as lamp and scale arrangement. Lamp and scale arrangement. You can see one lamp is there, and above which we have a scale. And for how we are using this, it is only for measuring the oscillation. Actually that lamp and scale arrangement is nothing to do with this torsional pendulum, right? This is what, only the torsional pendulum. This is only the arrangement to measure the oscillations. Okay, so to measure the oscillations, what we have done, we have attached one mirror on this particular torsional pendulum, right? You can see this is a mirror. Now from the lamp and scale arrangement apparatus, what we are doing, the lamp is focused on this mirror. The lamp is focused on this mirror, and the reflection of mirror, or the reflection of light from this mirror is now focused on that scale. That means we will find a spot which is moving on the scale. We will find a spot which is moving on the scale. If that disc is completely at rest position, then that spot is at the center point. That spot is at the center point of that scale. Actually, if you do this in a dark room, then you will find exactly clear the spot. Again, also I can see the spot, but I know you cannot see because of the what we can say the resolution and all this, right? But what I want to say you just understand the methodology, right? Once you switch off these lights, you can see the that spot also, right? But so what I am saying, so that spot, when the disc is at rest position, it should stop at the center of that particular scale, and it is there. Now as we rotate the disc, that means as we set the disc into the oscillation, what happens, that spot, that mirror also moving with the disc, the mirror also taking oscillations along with the disc, because it is also, or it is already fixed on the disc. So what happens, the as mirror is taking oscillation, ultimately the image of that mirror, that means that spot, is also taking oscillations on the scale, right? And there you can measure. Now let us consider that spot is now at the initially 0. So I will set it into the oscillation, and yes, while setting into the oscillation, you should keep in mind that spot should not go out of the scale, right? Then and then we can measure the oscillation. Therefore you have to give the small oscillation, not the longer or the larger amplitude oscillations. Now yes, the spot is moving, or the spot is only playing in the scale or on the scale. So I can say, now see, the disc is oscillating. I don't know you can see or not. I hope you can see, because this is what the small oscillation. So the spot is at now this position, I can count it as 0. Now spot is moving to the other extreme position, then to the this same 1. Likewise it goes to there again 2. Likewise, by using the spot you can count the oscillation. Now I hope you got the idea. Only to measure the oscillation we have this lamp and scale arrangement, otherwise it is having or it do not have any concern with this particular our torsional pendulum, right? So this arrangement you can use in some another apparatus also, maybe we will use in some another practical also, only to measure the oscillations, right? So the spot is moving, or a spot is taking oscillation, that means ultimately our disc is taking oscillation. Now once you set the disc into oscillation, just forget about this disc, just focus on the spot. You count the spot, how much we want the oscillation, 20 or 30, maybe 20 oscillations. So yes, 0, 1, then 2, then 3 and 4. So likewise for 20 oscillations, stop the stopwatch, whatever may be the time required, that is what time required for 20 oscillations. Likewise we have to take 3 different sets of reading, or we can say 3 trials, right? So once you got the 3 trials, that means time required for 20 oscillation, take the mean of those 3 trials. So maybe it is some 40 or 100 seconds, that is what the time required, or mean time required to take this disc 20 oscillation. But actually what we want in the formula, we want capital T, that is time period, and therefore what we will do, we know we should divide that by 20, and that will get the time period. Once you got the time period, other observations we already found, and then all these values we have to substitute in the formula, and we have to find the modulus of rigidity of this material of wire, right? So let's move towards the calculation part. Yes, after taking 3 different readings, so for the first trial we required 110 seconds for 20 oscillations, that is what I have noted here, and for the second trial we got 111 seconds, this is what T1, this is T2. For T3 again we got the 110 seconds for 20 oscillations, right? Now if we take its a mean, then that will be the T, which is in again second, so it is 110.3. that means for 20 oscillations we require these many seconds, and yes, for one oscillation just divide it by 20, so we got the capital T, and which is nothing but the time period, and this one is 5.515. this is what the time period required for one oscillation, time required for one oscillation, we call it as time period. Now let us see how to find the radius of wire. So since this wire, I told you this is a very thin wire, and of which we can find the radius by using screw gauge. So we have to take the screw gauge, and attach it or fix it at 3 different places of the wire, so that we will have the more accurate radius. And yes, after that we have to take the main scale reading, then circular scale reading, and the least count of screw gauge is 0.001 centimeter. And if we take these 3 trials, we got actually this is what the diameter, because we are fixing the wire by using screw gauge from outer side. So actually this is what diameter, we can write d1, d2 and d3. After taking its mean, we got the mean diameter. So this is what the diameter. And yes, radius again diameter divided by 2. So we got actually this is the radius 0.02665 centimeter. This is what the radius of the experimental wire, right? Earlier we got the radius of the disc, right? So this is what the radius of wire. And length of the wire we can measure directly. This is what the length of the wire, which is 19.5 centimeter. And as I told you, to find the radius of the disc, we have to take a thread and first of all measure its circumference, and from the circumference we can find the radius. So that is what we have found here. Yes, so circumference is actually 40 centimeter, and 2 pi r is equal to 40 centimeter, and from that we get the value of r, that is 6.3694. So 6.369, I will write here 6.369 centimeter. So all the observations we got, because here is what the radius of the wire, this is radius of the disc, this is length of the wire, and this is time period. So no worries, we can substitute it in the formula, and the formula is here. It is 4 pi L r square m. Already we know this m is 1150 gram. So all the things we are putting in CGS unit, so that's why no worries of the unit conversion. And T, yes, we got, R also we got. So after substituting all the values, we can find the modulus of rigidity of given wire, and here which is found to be 7.446 into 10 raised to 11 dyne per centimeter square. Maybe this magnitude will change according or as the person changes, or as we can say the apparatus changes, but generally it is in the order of 10 raised to 11. All these force constant, whether it is modulus of rigidity or Young's modulus, it is in CGS unit, it is in the order of 10 raised to 11 dyne per centimeter square. So yes, this is what we have to do, and lastly we have to write the result. The modulus of rigidity of material of the experimental wire is found to be 7.44 into 10 raised to 11 dyne per centimeter square. Yes, so yes friends, this is all about the torsional pendulum experiment, and next experiment we will see in the next video. Till then, you just watch all the videos, and if you feel this is value addition, then like our video, share with your friends, subscribe to our channel and press the bell icon, so that you will get the notifications as well as I will post the next video. Thank you so much for watching.